Let's take a look at this example here. So we have S equal to this set of three vectors. We want to find the dimension of the span of the set of vectors in S. So how do we go about doing this? So remember, a dimension is the number of vectors in a basis for the vector space. So the vector space we're looking at here is span of S. So we want to see how many vectors are in a basis for this set of vectors. Okay. Now, a basis has to do two things. It has to span the vector space, and it has to be the set of vectors has to be linearly independent. Now, box number one, spanning the vector space, we're good with. We've done. This satisfies by definition, right? Because the vector space is the span of S. We're taking the span of these vectors as our vector space, so of course these vectors span that space. That's how we're defining the space. Okay? But what we do need to do is we need to see, are these vectors linearly independent? Or do we have any redundant vectors that I can take out? All right. So remember, a set of vectors are going to be linearly independent. Let me give these names. Let's say v1, v2, v3. These three vectors are going to be linearly independent. If when we look at the homogeneous system, a1, v1 plus a2, v2 plus a3, v3 equals a zero vector, if this has only the trivial solution, the only values for a1, a2, and a3 that solve this equation is the trivial solution where a1, a2, a3 all equal 0, then the vectors are linearly independent. Okay? If there is another set of values for a1, a2, and a3 other than just the trivial solution, then the vectors are linearly dependent. So we want to see what the solution to this equation looks like. Okay, remember, we can translate this equation into its matrix equation, where the columns of the matrix are the vectors. Multiplied by our scalar coefficients, a1, a2, a3, equals the zero vector. Okay? So it's a linear system of equations, which means what we want to do to solve this is we want to take our coefficient matrix, this matrix here, and normally we'd take the augmented part, and we'd augment it with what's ever on this side. In this case, it's just zero, though, right? The zero vector. And usually when we have the zero vector over here, we don't even bother adding an augmented part, right? So I'm just going to take this matrix here and find its reduced row echelon form to see if we have just one solution to the system or more than one solution. Okay? So vectors v1, v2, v3. So I'm going to, let's call it matrix A. So my columns are vectors v1, v2, and v3. Okay? So these vectors right here. So if I put them together, I get my matrix. So v1 is -4, -3, -2. First vector is my first column of my matrix. Second vector is my second column of my matrix. Third vector is my third column of my matrix. Okay, so this is the matrix I'm going to put into the calculator. -4, hold on, -4, 6, -6, that's the first row. Second row, -3, 2, -2. And last row, -2, -2, 2. And the matrix, let's get the computer to put it into reduced row echelon form for us. And there it is. reduced row echelon form, we get the matrix 1, 0, 0, 0, 1, negative 1, 0, 0, 0. Okay? Now we want to see if that homogeneous equation, where the augmented part is all zeros, has just one solution or infinitely many solutions. So as we look at this, we should be able to pretty immediately see that we will have infinitely many solutions, because we have a column that does not have a leading one in it. Remember, our leading ones are this one and this one, right? In row 1, this is the first non-zero entry. In row 2, this is the first non-zero entry. In row 3, I don't have any non-zero entries, so I don't have any leading entries. The only entry that's not a leading entry is this entry right here. Okay, this is not a leading entry. It's not the start of a row. It's not the first non-zero entry in its row. And so the columns with non-zero entries correspond to free variables. And if I have a free variable, that means I have infinitely many solutions. Okay? If I have infinitely many solutions, then the trivial solution is not the only solution to the system. It's not a1 equals 0, a2 equals 0, a3 equals 0. Those aren't the only values that are going to work here. There are infinitely many possibilities. Okay? Okay. So the vectors in this case are linearly dependent. Which means I don't have a basis, right? They span the space, but they are not a basis because they are linearly dependent. I need them to be linearly independent to have a basis. So the question now is, which is the redundant vector? Which can I take out so that I still span the same space? Okay? Well, this same matrix actually gives us all the information that we need. What was our free variable again? Well, this one. The free variables are free because it's the extra information that corresponds to the redundant vectors. Okay? So the third column, the variable in the third column, is the free variable. So the vector in the third column of our original matrix is a redundant vector. If I get rid of that vector, then the other two vectors will be linearly independent. So if I get rid of that, then I row reduce, I get this. There are no free variables once I get this. Okay? Which means the trivial solution would be the only solution. So when you are looking for redundant vectors, you want to look for the columns that correspond to free variables. They're redundant. The columns that have a leading one are not redundant. In this case, I have two columns with a leading one. So the two vectors in these two columns, these two vectors right here, are all that I need to form the basis. This guy, this vector, is redundant. Okay? So the basis for this set of vectors, for this span, is just those first two. These columns have a leading one. That means the first two vectors are not redundant. Because I have a leading one in the first column and the second column. That's the first two vectors. It's two vectors form a basis. Let's put it that way. Okay. This column right here, this column has a free variable or corresponds to a free variable. the corresponding vector is redundant. The corresponding vector is redundant. Okay? And so my two basis vectors for this space, these two vectors form a basis. The dimension is just how many vectors are in the basis. So the dimension is 2, right? So the dimension of the span of S is 2. And because, by the way, the dimension is 2, we know what kind of geometry this span is going to give us. A vector space with dimension 2 is a plane, right? That's a two-dimensional surface. So span of S is a plane.